Afternoon, everyone. Thank you for being with us on this afternoon. Welcome to another seminar hosted by the Data Science Across Disciplines Research Group. Today's presentation will be given by Prof. Moulay Akhloufi, who is the head of the Perception, Robotics and Intelligent Machines Group in the Department of Computer Science at the University of Moncton. So his research and that of the research group that he heads focuses on machine learning, deep learning, computer and robot vision, drone vision, augmented reality, and intelligent machines. And their applications currently on a variety of different areas, such as defense and security, medical diagnosis, intelligent robotics, and smart sensing, as well as sport analytics and recommendation systems. So thank you very much for being here with us, Moulay, and we look forward to your presentation.
Thank you for inviting me. So just to say that my presentation will be high level, since I don't know all what you know, what you don't know. So I'll keep it high level, giving an idea about the type of research, and we are mainly focused on applied research here in the prime research group. So let's start. As you can see in my first slide, we focus on deep learning, computer vision, imaging, drones, robotics, optimizing using high performance computing with different applications such as security and defense, medical applications, fintech, industry. I will give some examples of what we have done in recent years. Of course, I would be open to questions if you have questions related to that. I will not go deeper in the theory. I will keep it in the application side, since we will show different type of applications and we don't have time probably to go deeper in all the architecture for all the applications. So let's start at Prime AI. As Charis presented, we are here located in University of Moncton in the New Brunswick province in Canada. And our group started when I joined the University of Moncton in 2016. I was working in industry before. And this group is focused on machine learning, where we work in deep learning applications, big data analytics, natural language processing, AI at the edge, including smart sensing, IoT, and things like that. Also applications in computer vision, which includes medical imaging, biometrics, machine vision, and industrial vision, as I will show in some of the applications. And robotics application, where we have autonomous navigation, UAV, UGV, industrial robotics also are part of our work. So this is the lab when nobody is in the lab. So this is one of our labs. We have now with the AI center that just started last month, more spaces. This is the old lab. We have it. We have it still because we need the spaces, and we have another for robotics. You can see some of the drones. These ones are. You can buy them I mean, it's a hobby drone, so we use them for testing outdoor. They can run outdoor, so it's interesting to do some tests. So applications area are various. We have, for example, in the upper set, you can see manufacturing. You will see some of the work we do in food processing. It's really down to earth application where we are building a system which is not available off the shelves of the companies, building that for commercialization purposes, of course. And we are helping them with the computer vision, AI part, and of course, robot vision, combining vision with robotics. We have projects in fintech. We have an ongoing project with insurance to evaluate the risk of the clients. So if you go and ask for life insurance, you can the AI evaluate your risk depending on many data, and this way you can have your what the cost of your life insurance, for example. So we are doing work on that. We are also doing work in finance. We have completed the work on project management. This is a really interesting work. Unfortunately, we cannot publish right now. There is an embargo on that, but the idea is if you have people in your company, depending on the project, on the type of the project, they can work better together. For example, I don't know, person X with person Y can work together better for web programming. However, if you have an AI application, probably person A with person Y can work better. So the idea here is to have an idea about the performance of your team based on projects, so you can ask those people to work on specific projects and be more productive, for example. And of course, this is related at the same time to team performance. We in the downside, you see telecom applications. We have some projects in the telecom application, sport rehabilitation. I will show some on the sports. Video surveillance, so we have defense and security. I will show some of the applications. And on for healthcare, we have a lot of work dealing with medical imaging right now. I will show some of the applications. Also using omics, we are working with the Atlantic Cancer Research Institute here in Moncton to develop a multi-omics AI system which predicts your probability of having cancer in the future, so you can have personalized treatments to avoid as much as possible the consequences related to this disease. So I will be here. I will give a brief overview of the techniques we are using. I will not go in deep about all these techniques. Probably some of you know already those techniques in deep learning. Some probably know, but it's about probably 2/3 or more of a deep learning course. So I will be brief. So I will be talking about CNNs, convolutional neural networks. These networks, what they do is just learn convolutions to extract features, and from, for example, an image in the input, you can classify. These techniques are also used for segmentation. I will show also some examples. For example, if you have as an input an image, you can have a mask as output, and the mask will locate specific things that you are looking for depending on the training you have done. And this is an encoder decoder like architecture where you have a lot of convolutions, and these convolutions are learned through training using this type of networks. I will be talking about recurrent neural network, and these network are, you can have different cells. The most popular are long short-term memory and gated recurrent units. With these networks learn some specific features, and you can put them in cascade one after another, like we see here in the image below, and they can be bidirectional, so you can learn normal time order and inverse order, and this is very useful in some kind of applications, as I will show later. I'll be talking about transformers. This is a hot subject these years, same in 2020 and 2021, and the decoder, the transformers are encoder-decoder-like architectures in many of the applications, but you can use only the decoder or the encoder depending on your application, or the two. And the idea here is to use multi-head attention that can learn. For example, when I was talking about recurrent neural network, it works on time series, but it's limited on the amount of data they can process. However, transformers, they were built to process infinite correlation between data, which is useful in some applications. I will show some of the uses of transformers we have done in some of the applications. I will talk about reinforcement learning. This is another way to train your algorithms. And the idea here is to give reward. When you train a system through observation, you see what's happening. For example, it can be an image, and based on that, if your target is achieved, you give a reward, positive reward. If it's not achieved, you give a negative reward. It's more complex than that, but the actions will be learned through rewarding the good actions and giving negative reward to the bad actions, and your algorithm is trained like that. And you can use, for example, like the application will be showing intersection over union to decide of the reward you are giving to your system, and through that your algorithm learns to do just the good actions to get the best rewards possible. And this way you train an algorithm, and I will be showing that on a drone chasing another drone using the measure of intersection over union to achieve this training, and to do after that the testing. So let's start first with an industrial marine application. As I said, this one is down to earth. Here in New Brunswick, we have a lot of lobsters. I don't know if you have lobsters in your side, but these cost a lot. I mean, and people look for that. And as you can see in a plant, people are doing this job manually. And the idea is to build a robot that can do it using computer vision based on extracting some specific features using deep learning and measuring in 3D the different features of this lobster. So you can control the quality, and after that you can pick and cut the different parts of the lobster. And the idea also is to optimize the algorithms to run at the edge in platforms such as the NVIDIA Xavier Jetson, which is a small embedded platform. It's not a large computer, because in a plant it can be difficult to have these large servers running. It's not useful. So different features are extracted with the company. We designed also a gripper, specific gripper for these species, because it's difficult to handle. These are living species. They are not how you say that, they are soft, so they are it's difficult to handle with the standard grippers. And as you see, with the idea is to build, you can see here the design of the machine, and the idea is from the lobster you can cut it and process it for commercialization in shops, for example. So you can see here the other laboratory we have, where we are doing these tests with the robot, conveyor, controller, etc. So this is part of this large prototype, and we are doing the different parts, and the company is integrating everything to build this machine. One of the projects we have done with the partner in France, it's a research institute which works in environment, and one of the species they are monitoring, and this species is very present in Mediterranean Sea, North Africa, as you can see here. And the species is called corb or brown migger. That's another name in English. And the idea is from audio signals, but they put microphones in the water, underwater, and they hear the sounds, and of course you have the sounds of the waves, the boats, etc. So a lot of noise, and from this noise you want to detect the species. So you can see here the spectrograms, and we have used the spectrograms to detect the species, and we achieved an F1 score of 95% using a convolutional neural network to learn from images. So the spectrogram is used an image as an input, and from that we learn the sound of the species versus the sound, the noise, and we are able to do that. We worked with 90,000 images as training with different augmentations, and now in fact today or tomorrow we'll have like 372,000 audio signals that they captured the last summer in the Mediterranean Sea. So this is the kind of signals or spectrograms that you can get, and from those you can you need to detect if it's the species or not. And as you can see, there is a lot of noise, and being able to process that with the F1 score of 95% is a very high score. Until now, they weren't able to do that with signal processing, classical techniques. So now we have state-of-the-art results using deep learning and convolutional neural network. Another work we have done related to fish is the fish classification, and this is for monitoring overfishing using onboard camera in the United States, and it's starting also in Canada. The idea is to put cameras on board of boats. These images will be monitored by humans. However, the idea is to use AI for detecting the specific fish. And here we are interested in this kind of fish. These images were captured in the Northern Sea of Canada, and they were taken by Nature Conservancy California. And with COVID, Fisheries and Oceans Canada, which are responsible of monitoring overfishing, they decided to, since they cannot send observers to boats, the idea is to do more and more of these kind of techniques and use AI in the future to do that. So you can see here images taken at night time with the different noise. It's difficult to see the fish. Sometimes there is occlusions, and still we have a top one score with 96% accuracy, more than 96% accuracy. And if we are looking for top two, so when the fish is not in the first position, the right fish it's in the second position, and probabilities are close between the first and second, we are close to 99% accuracy. So another area of applications, as I said, which show a lot of areas of application. I will step to remote sensing. One of the works we are doing is related to environment too, and the idea here is to monitor coastlines. So here we are in the Atlantic Sea, and there is a lot of erosion problems, etc. And the government here, the government of the province of New Brunswick, take aerial pictures with UAVs. In the past, they used the planes, and the idea is to detect the position of the coastline. And this job is done manually because the techniques available right now using image processing are not efficient, and this is time consuming. So the idea here, we are working with the company to develop a solution that uses deep learning. We published a paper on that in April, and the idea here is to detect automatically using convolutional neural network, but this time for segmentation. As I shown, we have also CNNs for doing segmentation. So from the input image, you have the mask, and this gives you the position of your coastline. And we have an F1 score of close to 95%. In fact, with the last result, we have over that. And this is one of the first results we had using these techniques for coastlines detection. Another work for remote sensing is the idea of detecting icebergs and ships. And as you can see, this is also in Canada, here in Prince Edward Island and St. John here. You have these oil platforms, and for oil platforms, when there is an iceberg, I mean, it's a danger for the oil platforms, and you can have some bad consequences if there is an accident between an iceberg and oil platform. And the idea here is to detect icebergs before they come closer to the oil platform, so you can intervene and avoid this kind of incidents. Of course, we don't. I mean, ships are not a problem. So the idea is it's an iceberg or ship using radar satellite images. And you can see here the images are not very good. Still, we have an accuracy of 91% detecting if it's an iceberg or a ship. And you can see here from true positive, false positive, it's difficult to detect. We're using these images, and you can see here true negative, false negative. Sometimes they are close and it's difficult. Still, the algorithm is this algorithm is also a convolutional neural network, is capable to get an accuracy of 91%. This also was published about 2 years ago in a conference. Another work we are doing in remote sensing is using UAVs to estimate the yield in for precision agriculture. We have accuracies over 90% to count, not only to estimate, but to count exactly the productions. And this is used in different type of productions, of course, and sometimes some of the productions are difficult because on the way the plant is growing, and it's difficult to, as you can see there, sometimes when the plant grow, there is some intersections between two plants, and you can have some problems related to that. Now I will step to security and defense, and we'll go show some examples. For example, we have done some work using for violence detection, and the idea here was to this work was done with the company called Rehati Security, located in British Columbia, and this company built software to monitor internet. And the idea here is, for example, in social media, some people put some violence videos, and the moderators the human moderators are not able to check all these videos and images. So here the idea is to have a system that can detect if there is something wrong and send the alert to humans, so a human is in the loop to monitor if this is violence, to remove from the social media, or if it's correct and you can keep it. And our algorithms now have a very high accuracy using some available public data sets. As you can see, this is the last algorithm we have developed. It combines both convolutional neural network, recurrent neural networks. As you can see here, we have GRU, gated recurrent unit, LSTM also in this architecture. And of course, we have used in this last one optical flow computed using convolutional neural networks. When you see the accuracies for the popular hockey dataset, we have 99% accuracy. For violent flow, the best one wasn't with the last approach, was with the one without optical flow, given 95.5% accuracy. And for real life, this is another data set, more recent. We have more than 96% accuracy on detecting violence or fight in video. I will show you here some examples of the type of video we are working on. So here, the part which is in green here is good detection. In red, in my right, you have these bad classifications. So let's see the good classifications here. This one was detected as fight, and as of course it's obvious it's a fight, right? And here you have another sequence below that was detected as fight during a baseball match, and obviously it's a fight, right? So in the upper side here you have a video of a fight, but it wasn't detected as a fight, and you can see that the problem is mainly the quality of the image. It's very blurry, and we cannot really detect what's happening there. So it was the algorithm wasn't able to detect the fight in this video. The other one that was detected as fight, and it is not, is this one of a soccer player who scored, and you know, his teammates are happy, and they are joining him running. The algorithms detect that as fight. So here is the sequence, and it was detected at fights. However, it's not the case, but you can understand why the algorithm has detected this as fight. Another application we have here, so he is related to crowd behavior. We did this work with the company here in New Brunswick, which is now part of a large company in Ontario. And what they are building is a way to detect if something is wrong. For example, if you have an event with a lot of people, a lot of crowd, and there is fight, you need to find that and send the security people before you have a general fight between every people. And We have modified the algorithms to use it for counting people, as you can see in the upper side in my right. So we can also count the heads of the people, and this can be useful in various applications. In security, we have also worked on securing large perimeters. And here, for example, like if you say airport, if you have someone coming from, I don't know, from some part of the airport which is not supposed to be there, and he is at a distance and you don't have a physical zoom, you can virtually zoom using deep learning and super resolution. So if you just zoom, you will have these blurry images, so you were not able to recognize the person. And we have developed a solution that super resolves the image so you can have a good recognition rate. And we can see here different applications in the near infrared, in the long wave thermal infrared, and the visible spectrum. So the first column, you have the lower resolution image. The second column, you have the classical techniques for interpolation to get higher resolution. And the third column is our results. And the ground truth is the last column. And you can see that there is these images look closer what we have developed compared to the ground truth. And we tested this approach with face recognition in the visible spectrum, and we get top one accuracy of 99% in a data set where for access control we have 72 individuals. So this one was for 16 time super resolution for this image. We have published some work on that, but we also used this to develop 64 times increase of resolution. And you can see here a small image. So if you zoom, you lose your object. Here, the ground truth, and I can show, for example, with the classical techniques, you are losing your target or your object. With our approach, we have the object there, and with the ground truth, you can see that the object is there. So with the technique we have developed, we are able to locate this technique. And these techniques are based on generative adversarial networks, which use convolutional neural networks, of course. Another work we have done is related to GPS denied navigation using UAV. And you can see in the upper image, it's not in simulation, it's in real life. We took about 10 kilometers flight and we simulated the losing the GPS, and we were able to get back. So in this case, we have used classical invariant features from computer vision adapted to this type of application. And you can see here that we have been able to get back to our starting position with an error of 25 meters, which is very good when you are losing your GPS and you don't have any other means to get your way back other than visual images and features. And you can see here the images and the features which are collected, and in the circle you see what we are predicting, because in fact we are using also what we call particle filters that predict from our current position which to look next. Okay, so this helps select just the most important images in our database where to look for finding our next position, so to move the UAV. This one is about UAV tracking another UAV or chasing another UAV. And in this one, you are using reinforcement learning. And what we developed is also a deep search area proposal based on adaptation of particle filters. And you can see here the idea, and this was tested also in our campus in real life situations, not only in simulation. We did also some work in simulation, published this year. And you can see here the idea is to locate the drone and to track it. And they can show here in the video. So you can see that you detect the UAV So this UAV, the first one, is maneuvered by human trying to escape, and the second one is keeping this drone on target and following the drone in real time. So you can see that the performance is pretty good in real life scenario. This is the campus where we work here in University of Moncton. And with the search area proposal, we were able to improve the performance in detecting the farther objects because they are very small in the image, and the deep learning is not that good when, especially object locations, when the objects are very small. So with search area proposal, we improved that. Another work related to security is about forest fires, and you know, when you have, this is some of the work we have done with the Université de Corsica in France, and the idea is to extract important characteristics of the fires using stereo images, and this information is input to the mathematical model for fire prediction to predict the propagation of the fire or the spread of the fire over time. And we continued recently working on deep segmentation, because if you want to build this 3D model using stereo, you need to segment the shape of your fire, and these fires are in non-controlled environment, as you can see here, because we are talking about wildland fires or forest fires. And you can see here the ground truth versus what our algorithms. So recently, this one is not published yet, but a modification of efficient segmentation was, we were able to get an F1 score of 95%. And we developed, this is the journal paper is prepared right now. We will be submitting it in probably this month. We have developed what we call Transfire. It's transformers used for fire segmentation, and we have right now probably the highest score at my knowledge on segmenting forest fires with 97.5% F1 score. And one of the uses of that is using UAV, and you can see here, this is aerial images taken by helicopter, and you can see that we are able to detect the fire and segment the area where the fire is present. Another thing we have tested is, as I said, when you take these images and take this data, the idea is to predict the spread of the fire or the propagation of the fire over time. So what we say, okay, let's, this is done with mathematical models, of course, and the mathematicians and physicians are working on that. And what we asked ourselves, are we able to do it with machine learning and deep learning? And the answer is yes, because we were able to build this one. In fact, we are preparing, we published the paper in a conference, and we are preparing an improvement, the new result for a journal paper. So we have the idea was to take satellite images and also elevation map, different information about historical fires, and of course other information such as humidity, pressure, temperature, etc., and input that to an encoder-decoder deep neural network based on what we call UNet. It's based on that, and we were able to predict the propagation of the fire in over 24 hours, where the fire will be in 24 hours, with an F1 score of 97.4%. An area under curve of 98%, more than 98%, and accuracy over 96%, which is something very high. And these data were taken at Rocky Mountain area in the United States. Also related to security, but this time is about text. And this work also was done with the company Rehati Security in British Columbia, which built the software for monitoring online content. And the idea here is to detect toxic content online. And we built an algorithm that detects misogyny in social media with different languages. And you can see here in the upper part, you have English, Spanish, French, Arabic, Italian, Hindi. However, in some cases, like for example, French misogyny, we don't have many cases, so the algorithm wasn't able to perform as well as in English or other languages. And in the lower part, we have used the annotation-based bidirectional LSTM. So we added attention to a bidirectional long short-term memory, and we were able to get higher accuracies. This is currently the highest accuracy for misogyny detection in different languages. Some languages we don't have the F1 score as we would like, because we don't have as many cases as we would like in the dataset. And also for the category, for example, when you have misogyny, we did that in English because the only dataset that has the different category is in English. So we are able to get an accuracy of 90.9% to detect exactly what type of misogyny or what category of misogyny is in the text. And this, of course, as I said, it will be later implemented in the software of the company. And we submitted a paper, of course, with the same company. For monitoring online content, they are working on detecting nudity. Of course, I don't show that here, but the idea is, for example, in some social media or some gaming sites dedicated to children, you are not supposed to post nudity content there. And sometimes it happens, and they have a lot of problems. As I said, a human cannot monitor all the contents, and the idea is to build software that can help them do that. So we have developed a body parts detection algorithm based on poses. From poses we detect the parts, and we have average accuracy of 89%, which is high because for example, depending on the parts, the ones that are lower are ankle and knee, but these are not the area which we are looking for to detect nudity. And the same algorithm is adapted right now to detect child pornography online to monitor social media websites. So now I will step to medical imaging applications that we are doing. One of them is detection of eye diseases. And we are interested to diabetic retinopathy, age-related macular degeneration, and glaucoma, because this causes the blindness in the developed world. I mean, the majority of blindness is caused by these diseases. So we have developed the one in blue here, age, AMD, and diabetic retinopathy. We have solution, and we have now, I will not show here, but we have now some results related to glaucoma as well. And the idea here for macular edema, we want to detect these kind of features that happened in the retina. Similar things for the age-related macular degeneration. We can have choroidal neovascularization. Sorry, it's complex to say the choroidal neovascularization, and the drusen, which is another case when you have accumulations of debris under the retina. So the idea here is there is a lot of machine image processing and computer vision techniques to extract features like hard exudates, soft exudates, microaneurysms, and hemorrhage to detect these kind of diseases. However, our objective was to build an end-to-end deep learning algorithm to do the job and to grade, for example, for diabetic retinopathy using retinal images. The idea here is not just to detect the presence or absence of diabetic retinopathy, but also to grade with different grades that are used by ophthalmologists. You can see here, in addition, we have an explainability model. So when we detect a retinopathy, we highlight the areas where to look for these signs. So for example, ophthalmologists can have a look and see where the signs are for the disease and why the algorithm decided that this image contains diabetic retinopathy. We have, for diabetic retinopathy, as I said, we are able to detect grades. So normal, mild, moderate, severe, and proliferative. And we have as a result, an area under curve of 98.6% on more than 80,000 images, with a specificity of 97%, sensitivity of 95.8%. And if we are interested in what ophthalmologists are looking for, like referable diabetic retinopathy, we have an IUC of 98%, and vision threatening diabetic retinopathy, we have an IUC of 99%. As since with these high scores, of course, it's obvious that we detect with high precision the signs of the disease, as we can see in the images in my right. For DME and AMD, diabetic macular edema and age-related macular degeneration, we use OCT images. The OCT takes the volume of the retina, and you can detect different diseases. Of course, the apparatus costs some money. You know, these machines cost some money. You cannot find them in rural area. However, you can find them in hospitals and you know, in clinics where they have this kind of machines. And for OCT, we are able to detect, as I said, different aspect of age-related macular degeneration, like choroidal neovascularization, diabetic macular edema, drusen, and of course the normal cases. And as I said, the explainability show you where to look for the signs, and even the normal, it shows you that this part is normal. So, and the idea here is not just to give the answer that there is specific disease, but also to give you where to look for the signs. Similarly, here we have the results with OCT. We have an area under curve of 99.8%. This is very high and was tested on more than 80,000 images. Specificity of 98.7%, sensitivity of 98.4%. And with these high results, it's obvious also that we can locate precisely the signs of the disease, as we can see in my right. This system, specifically the first one for diabetic retinopathy, was deployed in our website so people can use it. And this is the website address, can use it freely. Of course, now it's somehow slow because in the same server we are using another one for COVID-19 detection, as I will show in the following, but we are starting to build another server where we will deploy these models. Another work we have done in medical imaging is related to radiology and chest X-rays, and the idea is to detect different type of diseases using X-rays. In this work, we have more than 224,000 images coming from more than 65,000 patients. This is a data set that was released by Stanford University. And you have frontal and lateral images with 14 observations with different diseases like pleural effusion, cardiomegaly, lung opacity, etc. So the average for all these diseases, we have an area under curve of 96%, which is something very interesting. And of course, for some diseases like pleural effusion, we have 98% area under curve, which is high. The ones that the lowest are around 93-94% in the case of when there is no disease, for example. And this depends on the quality of the image. This is of course a convolutional neural network that is doing the job. Similar thing for the eye diseases, we are using a convolutional neural networks. We adapted those algorithms for detecting COVID-19 in chest X-rays, and what we have is the detection of the signs with explainability, the signs of the disease at the same time as the probability of the disease. And here we have a data set. We are close to 4,000 images now. And we have COVID-19 CXR images, normal images, and other pneumonia, because COVID-19 is pneumonia, but you have other viral and bacterial pneumonia, which is present, and we want to differentiate between them and COVID-19. For this work, we have now sensitivity of 97%, specificity of 94%, and an area under curve of 94%, which is pretty good, given that we are using 9 data sets with heterogeneous images. So the images are coming from different parts, and we are working on this work with the hospital in Ottawa, in Ontario, Hospital Montfort. They are bringing new images to our tests, and we are using available public images, so using 9 data sets to give these kind of results. The system is deployed online, so it can be used freely by everybody. As I said, it's done with the Montfort Hospital, and in the website you can test to detect COVID-19, and you have the explainability image, so you can see exactly where the signs of the disease are located. More recently, we have worked also in CT scans to detect COVID-19, and with really interesting results. So, for example, we have worked as a majority of people, they are working at image level. For example, when you take the computer tomography images, you have different slices. So these slices are, each one is an image. So a lot of publications are related to those slices. So we did it also. So we have a sensitivity of 94%, specificity of 91%, and area under curve of 98%. And also similarly, if you can see the images here, we locate where the signs of the disease are present. But also we have we have just one data set where we have this CT for specific patients. So for example, for one patient, you would have 100 or 200 slices, and you need to say if the patient has COVID-19 or not, which is more close to reality when someone goes to the hospital and we want to find if he has the disease or not. So we have at patient level sensitivity of 91%, specificity of 96%, and an area under curve of 93%. We have done also some work related to detecting COVID-19 on point of care ultrasound, but this one is preliminary. We have an area under curve of 99%, which is high. However, the number of images is limited, so more work needs to be done. There is not a huge number of POCUS images available right now, but we have found the one data set with enough images to rework our algorithms and see what kind of result we can get. Another work related to medical area is about detecting cells nuclei, and the idea here is to automate the extraction of the nuclei from the cells for DNA. So you can take these nuclei and extract the DNA for different type of applications. For now, humans are doing this job, and the idea is to automate the process as much as possible. To do that, you need to detect the nuclei, and we have developed a unit-based algorithm which is able to detect the nuclei in different type of images with an F1 score of 96% and an accuracy of close to 98%. Another work we are doing, this is preliminary for now, but we have very interesting result. It's with the Atlantic Cancer Research Institute, and here we are using multi-omics. We have a large data coming from proteomics and genomics and proteomics and other omics, and the idea here is from this data, are we able to predict if the person will develop a cancer? So we have historical data they captured over time for pancreatic cancer, for lung cancer, for prostate cancer, and now they are processing breast cancer as well, and we will be working on breast cancer. And we have, with this data, we are able to show that with omics, we are really able to predict with pretty good accuracy if someone can develop cancer. And for now, we have some over 98% accuracy on different type of, if we, as average, if we combine different cancers. Another application is AI for cybersecurity. This is recent. We are not specialists on cybersecurity. However, using AI for cybersecurity will be the future, I think, because you can be proactive. You don't wait for the antivirus to be available. You can detect something is wrong. One of the work we have done is detecting malware. And the idea is to convert malware in as an image. The idea was first proposed by University of Berkeley in the United States, and they used it. It was, I think, in '97 or something like that. So they used machine learning at that time, but now we are using deep learning with the new data set coming from Microsoft, and with this converting the bytes. The bytes data to images, and then inputting this image to a convolutional neural network to predict if it's malware or not. We have a detection accuracy of 97%, which is very good for this type of detection of malware. Another application, a recent one, is using transformers for cybersecurity. So we developed what we call MalBERT. It's malware based on BERT. BERT was proposed by Google, and we adapted that to detection of malware. So this is, at our knowledge, the first work using transformers for in cybersecurity, and we have pretty good results. For example, if we have a model which uses, the model combines pre-trained BERT to make classifications. So we have the binary classification. Binary is detecting if what you have, and we have worked, of course, with the dataset for applications on Android smartphones. So the idea here was to say, okay, binary classification, is it malware or not? So with that, we have a more than 97 accuracy for binary classification. But also we developed an algorithm, transformers-based algorithm, to detect the category of the malware. So as you can see here, we have like 1, 2, 3, 4, 5. So we have 10 types of malware, of categories, and we were able here in categorical classification to have 91% accuracy to detect not only malware, but what type of malware it is. Similar approaches are used for another application, which is very important. We just created an AI center with the NB Power. NB Power is in the energy company here in New Brunswick. And over the past, we have developed something that can be of interest to them, is detecting power line fault automatically. And this can be power line defect due to some defects in the line, or some malware, for example, or some hackers that try to cause faults in the power line. And the idea here is to monitor the signals, and from the signals detect if there is a possibility of faults in the near future. And we are using deep learning in an ensemble learning approach, so multiple models are combined together, and we have an accuracy of 97% of detecting if a power line fault will happen in the coming hours. So this is, we are in the last slide. So I think we are close to our, to the end of the presentation. So this one is multiple applications at once I will talk about. So one of my students was interested in autonomous driving. So we have developed a solution that combines both visual spectrum images and what we call event-based frames. So I'm not sure if you are familiar with the event camera. The event capture just the differences or the variation in the scene. So combining these two images, we developed deep CNN able to detect the steering angle during autonomous driving. And you can see here our work outperforms PilotNet, which was proposed by NVIDIA, and other works that used this kind of prediction in the past. And I have some videos, I think, here. Yeah. So we tested in different scenarios, for example, so I can move it faster, a little bit faster. Yeah. So you can see here in the lower side is during night. So the idea is to predict the steering angle during night. So the quality of the image, as you can see, is not that good, but we have the event camera and the visual spectrum camera, and the other one is during the day. And we give some results about the error. The error is given in terms of root mean square error in degrees between the ground truth, the position of the ground truth of the steering angle, and what we have predicted. As you can see, day, evening, and night results are very good compared to what was proposed in the literature. Other works we have done is about using poses for sport and rehabilitation. So we have used the 2D models and 3D pose estimation from monocular images. This is based on pose estimation, and the idea is to, for example, you can compute the angles of between your hands or your feet, etc., and the motion of the person. For rehabilitation, this can be very useful to see if the person is walking normally or not. As I said, we have worked also in insurance. I cannot give much detail apart that risk assessment in insurance is very important. So we are using predictive analytics and big data for that, and we have very good results. But for now, this is not, we didn't publish about this work. It's still confidential. Other work at the same level of still ongoing, so it's confidential. It's related to the use of NLP, natural language processing, and natural language understanding, and big data to predict the performance of the company. For example, if you have this memo and the report from companies, you can predict if the company will be doing well in the future, so you can invest or not. We are developing some predictive models for that with an industrial partners, right? So this finishes my presentation, and if you have any questions, so I'm available to answer those questions. Thank you.
Thank you, Moulay. Thank you very much for your presentation. I think there is a question that's come up from Luke Machowski. It's in the Q&A, and he asks, how much emphasis does the team put into the user experience for keeping the human in the loop to judge the outcome of the machine learning outputs?
Yeah, human in the loop is very important in specifically for some of the applications. For example, when you are talking about the medical area, for sure you need a human in the loop. But because at the there is rules, of course, but because I mean the diagnostic needs to be done by a physician. That's because the law is the law. That's it. And the other thing, when you are doing medical diagnosis, you need more just an algorithm that gives you something. You have to see it as a help. We are helping the physicians and not replacing the physicians. The idea here is to process or to see as much as patients as possible, but not to replace the physicians, so just to improve the process, in fact. But you will need human in the loop. Same thing for security. You cannot expect, for example, and I saw recently an article about people thinking about, okay, can we use weapons? I mean, machine learning controlled weapons. I don't think it's a good idea, because in paper can be very good. You have very good accuracy, etc., etc. But you know, the consequences can be bad, and this is something I will not recommend at all. You will need human in the loop. Human are not perfect, but still they can use their judgments, and you can say, okay, I will not just because there is a threat, I will send I don't know, bomb or something like that. You can think about it and find different ways to do it. Human in the loop is important. And similar thing for fintech. We have, I didn't talk about the project we have in banking and the one in insurance. The idea here is also to help them. So we will give prediction, we will give interpretability and explainability why these predictions were done, but at the end is the human who needs to make the decision. So in all this project, when in the beginning we say that to all our partners, and they are aware of that, so they know that this kind of things you need to keep human in the loop, of course.
Thank you. Oh, Luke has another question. What is the success rate of medical diagnostics of a new doctor? Is there any data like that to compare the results to? That's a very good question.
Yeah, I can talk about what tests that have been done in China, for example, for detecting lung cancer. I'm not sure if you are aware of that. They did a lot of, it was in 2019, I think, or 18, and they did a deep learning test predicting lung cancer. That when you have a tumor, you detect the tumors, and not all the tumors are malignant. So we have some benign tumors. And they tested physicians, radiologists versus deep learning, and deep learning outperformed everybody. We saw a paper published recently about COVID-19 in November by a team from Northwestern in the United States, and they tested with radiologists in Northwestern, and the deep learning model was outperformed what the physician has done as diagnosis. But of course, nobody has said if this is new people to the in the job or old people. That's why I think it's important. Deep learning, machine learning, AI is very important in these types of area, but we need to keep the human in the loop. We can improve the performance of the human, giving him some help. Still, we will need them in the loop. So even if someone showed that a new doctor is not as good as machine learning, I will prefer to talk to the doctor than having a robot saying to me, okay, you have that disease. I don't think it's good in the health area, at least.
Yeah. Now, I've seen similar statistics as well, where it's like the AI outperformed a doctor, but it's never indicated what is the experience level of the doctor, because at the end, that's what you're trying to replicate, right, in your AI. We've got another comment from Muzi. Thank you very much for an interesting talk. Well put. How does one get involved in these projects? I'm very interested.
The question is, you mean students or researchers?
I think at this point, probably anybody.
Anybody, right? Okay.
So this kind of work, what do you advise for a young professional, young academic student? How do they get involved in these kinds of projects?
Yeah, so I will talk in general, and then I will talk more specifically in our case. In general, you will need to know about machine learning, deep learning, and I will advise, for example, because I saw some examples of people jump into deep learning and thinking that deep learning can solve everything. And sometimes, you know, my background is computer vision, you know, so I worked a lot with classical techniques in computer vision, using machine learning with image processing, things like that. So when I work with images, I know what kind of features can talk more than others. And I think if you are working in some specific area, let's say computer vision, to give an example that I know much, you need to learn about the, so for example, in our university, we have the computer vision course, we have the machine learning, we have the deep learning course. So I advise to my student to start with the computer vision course, and we have image processing too. So you will know the classical techniques, you will understand everything about features, convolutions, what features that are more meaningful than others, etc. And then when you jump to deep learning and let the convolutional neural network do the job, even if it's an end-to-end, you have somehow an understanding of what can work best and what cannot work best. And when you analyze, I ask always my student to analyze the wrong classifications or the wrong segmentation, and to use their eyes and their brain to try to understand what was the reason behind these bad classifications and things like that. So when you have the background, the classical background, you can understand more. So my advice is, if you are interested in specific area, learn about first that area, like image processing for images, computer vision, and then deep learning. If you jump to deep learning, probably will have some good result, because deep learning works very well, and you have some examples, and you can just fine tune, and a lot of people do that. But if you don't understand the basics, probably you cannot perform better than others. So my advice is to learn about the techniques before going with the deep learning transformers and things like that. Otherwise, you cannot get very high results. And to get involved, as in our case, for example, we have many projects with different companies. More than 80% of our projects are with companies. We have other projects that are funded, and we can decide to do our own research as we like. And of course, our students, we are in the computer science department, but my background is electrical engineering. So mostly focused in computer engineering, but I mean, in Canada, your diploma is electrical engineering, and people that know to program can jump and work in this kind of projects. Mathematics is also a good advice to have a good understanding of mathematics. Otherwise, I mean, at least basics, algebra, matrix computations, and if you know about optimization, that's very good. I did courses in mathematical optimization, and this gives a better idea how to optimize the algorithms working at the mathematical optimization level, which can bring better results when you work with the different algorithms. I don't know if I answered the questions.
I'm not sure. Muzi, was that, if that's not what you wanted, then you can just ask another question. In the meantime, Moulay, I actually wanted to ask something quite specific. It was about the example you showed that had to do with trying to identify nudity. And you indicated there was a huge difference between the accuracy for shoulders and head versus knee and ankle, for instance. And I was just wondering, I mean, obviously there's the quality of the image that makes sense. Maybe the body parts are smaller, and so they're not as obvious. But why do you think that there was such a huge discrepancy in the accuracy between those different body parts?
Yeah, probably we don't. I think we see here some example. You see the position of the persons.
Yeah.
The position of the person sometimes make that your ankle or your knee are not visible as, for example, your head, okay, or your shoulders. That's the main reason. We have a lot of occlusions, and sometimes you have some part that are missing, or you have a feet hiding another feet, which make things very difficult. That were the main reasons for this kind of results.
The position of the body.
Position of the body was sometimes hard because the person is doing some sport or just relaxing, so you don't have the full body. I mean, if you have a frontal image, it's easy, but it's not always the case. Yeah.
Well, and especially if you're trying to detect online nudity that's inappropriate.
Exactly. Yeah.
Yeah. You see, if you understand how the algorithms work, then obviously you can easily bypass it, it seems. So it was interesting to see the difference in the accuracy. So thank you.
So, I mean, the positions will be will make things hard to detect. Still, we have a good accuracy, and they say if in this work also you need a human in the loop. But because I mean, let's think about it. You don't want to censor what is correct. Can be in text or in images. So you detect this kind of information and you send it to the human. The human will see if it's legitimate or not, because you don't want to block something legitimate because your algorithm is erroneous, for example, because it's not perfect. It's not 100%.
Yeah. Thank you. Are there any other questions from anybody online? Oh, Muzi says that yes, you've answered their question.
Yeah,
so
perfect.
thank you very much. All right. If there aren't any other questions from, oh, there is one from Luke. Oh no, a comment. He just says that was amazing and thank you very much, Moulay, which I agree.
My pleasure. Thank you.
Thank you very much for your time, and thank you very much for taking us through all these very, very interesting applications that you and your group are engaging with. And I'd also like to thank the audience that's with us, especially since it's quite a bit later in South Africa than it is there for you. And also, I just wanted to remind everybody that we will be having another seminar coming up in June. And our presenter will then be Professor Misha Siddhartha from the Department of Mathematics at ETH Zurich. And we look forward to seeing you all then. Thank you again, Moulay.
Thank you.
Have a good day.
Bye.
The University of Johannesburg, the future reimagined.